So as you know, there are three categories of cyclic loading. One is a fully reversed. That is what we do for doing the test, especially it is for the test generated using the rotating bending. That's the old times, but if you are doing axial, that's a different. R is equal -1. Doing an axial loading will be difficult. Forget of -1, even 0, unless R is equal to 0 and thin specimen. For thick specimen, there is no issue. But thin structure also you can do R is equal to minus, not -1, minus side, but you have to provide an anti-buckling guide to ensure that it doesn't buckle during the compression thing. But you have other type of categories which is called repeated and also called fluctuating, where mean stress are positive. When a mean component stress is added to the alternate component, in the example of B and C, the material fails at lower alternating stresses than it does under fully reversed loading. So if you do the testing and fully reversed, you will get some X number of cycles to failure for same material. But if you have a repeated load or fluctuating load, it will keep on repeated load will have some value which will be intermediate between the fully reversed and the fluctuating. It will take less number of cycles to fail because mean load is more. For cycle with other than R values, it is required to make correction to the stress range in order to be able to compare the cycles to the SN curve. So far we saw SN curve generated for smooth specimen R is equal to -1, but in practicality or reality, the structures will be subjected to variable amplitude loading, or even if you consider some example where it is subjected to constant amplitude loading, but need not be R is equal to -1. So in that case, we need to do the correction. We have seen the correction of SN curve at endurance limit correspond to the different load size and all, because your component is different from your test specimen. Now how to take care of the mean stress. So mean stress can have a significant effect on the failure due to fatigue and must be considered in combination with the alternating stress. So this is please remember, SN curve can be represented in y-axis as a stress amplitude, stress range, or S max. But very rarely you will get alternate stress SA in y-axis. But if you see MMPDS, it is always S max, and most of the time we will also presentation will be showing as S max, and that also for different stress concentration factor it will be based on net S max, not only S max. Only KT is equal to 1, your net S max and gross S max is same. Now you have seen the curve S equal mean equal to 0, which corresponds to R is equal to -1. For given stress level, this is the life. So this 2 10 to the power 5 C for example. But if you have a tensile mean stress, your SN curve comes down. So also your life is coming down for the same stress level. But in the case of compression, you do get a beneficial effect. That is what general understanding or thing. But usually there may not be much difference. The way it is exaggerating. See, 1 cycle to 1, this is log scale, that means 1 order of life, it may not be. It depends on like a case basis case. The tensile mean stress in general detrimental, while the compressive mean stress is beneficial and has negligible effect on the fatigue durability. And because most of the SN data used in analysis was produced under zero mean stress, therefore it is necessary to translate cycle with non-zero mean stress into equivalent cycle with zero. That I will explain you down the line. So even though you have a SN curve available experimental data, then unfortunately it may not be available for different R or different KT. So later on we will see KT means the notch effect, but even if you for smooth specimen, if you are trying to do a prediction of a component and without any KT notch effect, but smooth one, but different R. Either if you have is well and good, but sometimes you may not get a R curve, and you cannot extrapolate beyond whatever given in the data set. Interpolate you can do, say R is equal to 0 is there and R is equal to say R is equal to 0.5 is there. and you want to know what is the SN curve for R is equal to 0.25, you can do the interpolation. But if R is equal to 0.6, you cannot extrapolate. Okay, that is a general standard practice. No, it's not recommended to extrapolate the beyond the range of experimental data which has been tested. So in that case, one can use Baskin equation. That's a very novel equation. But Baskin equation is always referred to R is equal to -1. So obviously then in that case you have to do the correction, mean stress correction factor to that. This is very paradox results. Just observe it, which we generally overlook it when we take it for granted, but sometimes somebody will cut you, then you will get perplexed, but nothing to worry. So this is tested, this is came up during some technical review meeting between ADA and HL, where I was reviewing in the committee. So this question came, so that's what has been addressed. The issue is, this is MMPDS SN data, right? Curve. You see Kt is equal to 1, you have a different stress ratio. Okay. So what has been done, and luckily in MMPDS, to represent data, it is given in the equation, equivalent stress equation. So that means it's trying to represent the log cycle encompassing all the data. There you can see a lot of scatter thing, but obviously you can see what is the standard error estimated, and the R square is 82% only. So if people know what is R square? Hello? What is R square? You have to ask now. So new meteorology, don't take it for granted, then it will be half information knowledge. This earlier you have done it, probably you are not occurred to your mind. R square is a coefficient of correlation. When you have a set of experimental data and you are fitting a best fit line, obviously data, if all the data falls into the same straight line, y is equal to mx plus c, then R square is equal to 1. Perfectly it will be matching. If data is around above and below side of the things, and there's a difference between the predicted minus test to the square divided by number something, the R square thing. So it 82% means there are a lot of scatter. There is a thing. You can see the data is the scatter. Here, I don't know, some data there. Yeah. No. Scatter factors is to take into the account the variability into account due to the variability in the mechanical, I mean, say material properties, load, then you have analysis method. Yeah, that I will cover the scatter factor. This is the thing, how to judge your best fit line is how far up from the experimental data. If R square 1 is a perfect, you have set of data y versus x, there in the line, you fit a line exactly coming, it's a straight line, R square. The difference you are taking, no, because test result minus a prediction. Is it 0 means, that means that test result is lying in the predicted line. So R square you have to take some average of that and all. Okay, so anyway, this is fitting. Anyway, the idea is you can put, if you want in between some R value, you can substitute. That means it is given up to 0.5. If you want to get R is equal to 0.6, you cannot use this equation. You will get some value, but it's not recommended. So what test was done? At Kt is equal to 1, they did for S max is 200. Okay, this is KSI unfortunately, but okay, it can be converted. What did you see the previous slide? We saw that at positive stress ratio, positive mean stress is detrimental effect, right? Here, positive are more than R is equal to more positive R or mean stress, your life is decreasing, right? But here what do you see there? you are, of course, we are going from negative to positive, increasing R. But what the life shows is increasing. So it's a contradictory, right? So there's nothing wrong in that. The problem, the issue is when you plot with respect to SMAC in SN curve, you are using referring SN curve, you know for 150 R is equal to -1 here somewhere there. So as you decrease increasing R, you are getting more thing. But what we saw the previous slide is the range. Your SMAC stress range and R, they are interrelated. So it amounts to something, but to explain, one hand you are telling R is increasing, your detrimental effect, your life is decreasing, but here you are getting increasing because you are referring to graph of S max, not to the stress amplitude.